Hello, everyone. Good morning or good afternoon, depending on your time zone, and welcome. I'm so happy to be hosting this Research Spotlight Symposium today. The Research Spotlight series is a collaboration between us at Tobii and our customers to highlight groundbreaking research utilizing our eye tracking systems. This webinar series showcases current and ongoing work to hopefully give you inspiration, answer questions, and create networking opportunities. This webinar will be recorded, as always, so feel free to rewatch or share with students and colleagues. A link to the webinar recording will be sent via email within a few days. We have also hosted other webinars like this on a variety of topics in the past, which can all be found in our Tobii Resource Center. So this is our agenda for today. This research webinar has been organized with 4 researchers from the Collaborative Intelligence for Safety Critical Systems group. And their research explores how eye tracking technology is being leveraged to enhance safety, decision-making, and user experience in high-stakes environments. Each presenter will have 10 to 15 minutes to share about their research. We will have a roundtable Q&A session at the end where we can ask questions of all the presenters. So please feel free to ask questions in the question box in the GoToWebinar platform throughout the presentations, and we will address them in a group at the end. So we are highlighting research in human-machine interaction today, but we have customers across all research areas. So if you're looking for more inspiration on the unique and exciting uses of eye tracking to understand human visual attention, we've got it. Eye tracking provides a very rich data set from specific fixation metrics and saccades to eye-related biometrics like pupil diameter, eye openness, and blinks. As a note, if you're interested in learning more about our very new blink metrics that are coming out soon, please sign up for our webinar on November 19th, and you can find that at tobii.com/events. These metrics provide unique insights into the cognitive state of humans, including attention, decision-making, problem-solving, and more. Over the last 20 years, our products have been tested, proven, and cited in over 12,000 publications and counting, so we hope you join our ever-growing Tobii research family. For this webinar, our presenters have collected data using our screen-based and wearable eye tracking systems, so let me show you briefly how they work. There are typically 2 cameras for a screen-based system. We have near-infrared illuminators and algorithms. The cameras take photographic images of the eye up to 1200 hertz, so a sample about every 0.8 milliseconds. That's the top of our sampling rates. The illuminators create a corneal reflection on the eye, which then allows the algorithms to determine the pupil center to map where the participant is visually attending. And since all the stimuli are presented on screen, our software Tobii Pro Lab or our Tobii Pro SDK can automatically map the XY fixation coordinates onto those stimuli. Our Tobii wearable eye tracking systems are similar. They have these hardware components with 2 cameras per eye and 8 near-infrared illuminators. Our Tobii Pro Glasses 3 operate at 50 Hz or 100 Hz, so you receive an eye image and XY coordinates every 10 or 20 milliseconds. There's a scene camera in the front to capture where the participant's head's oriented, and on the recording end, you'll see the 3D gaze convergence point overlaid on the scene camera recording. The unit is powered by a lithium-ion battery, which can be comfortably worn for mobile research. Data is stored on an SD card and can be streamed live to watch through the eyes of your participants in real time. Then you can also analyze qualitative and quantitative data offline. This is an overview of our product portfolio with sampling rates up to 1200 Hz, as I mentioned before. All of these hardware, both in our screen-based and wearable portfolio, are compatible with our software, Tobii Pro Lab. Tobii Pro Lab is our software platform for design, recording, data inspection, and analysis. In addition, we have free software enablers in our Tobii Pro Glasses API and our Tobii Pro SDK. We also offer solutions together with partners, so if you're interested in synchronizing eye tracking data with other physiological data streams like EEG, GSR, heart rate, or more, you can use our systems. If you're not sure which system is right for you, our amazing sales team can help you find the right product fit. And finally, we're here to be your research partner. So we have a funding proposal assistance program, which is totally free. We will help you find and win grant money to fund your eye tracking purchase. Feel free to reach out to us with questions. And if you're a current customer, don't forget about our Tobii Connect portal. Prospective customers can also use this portal and download sample projects for Tobii Pro Lab, read our frequently asked questions, and more. Here are the links for the proposal assistance and our Connect portal here. And there's my email if you want to email me directly. Okay, so now I'm going to introduce our first speaker, who's Dr. Maria Chiara Leva. She's the head of the Human Factors in Safety and Sustainability Research Group at the Technological University of Dublin. We're so excited to learn more about your research, and I will invite her to join us now.
Thank you, Marisa. And thanks to Tobii for inviting us, but in general for being a great partner in some of the efforts that we are trying to put together in sharing our research. So as Marisa said, we have a group about human factors in safety and sustainability in TU Dublin. And as part of that group, we started doing some specific research in collaborative intelligence application, safety critical system. And I invited, basically, instead of me presenting those results, it's much better if the people that are been on the front line of collecting the data, analyzing the results, and battling with the challenges that are even in the interoperability of those resources for data collection, I've learned in this process. In fact, that's why my presentation is going to be rather short to introduce the framework and the project and the research group in which this research occurred, and these are some of the people that made it possible. So you have a sample of 3 of them present today. Inesh, who is going to be presenting some results from telerobotic, and then Amar from an experiment run in a control room setting, and Enrique that is working on in a traffic controller, with a traffic controller. So the idea is, why are we collecting eye tracking data in this context? Because basically, we've been inspired by this quote from Doherty that says, organizations that use machine to displace workers through automation will miss the full potential of AI. While tomorrow leaders are the ones that are able to transform operation in terms of collaboration and transform also the workforce. Now, for this paradigmatic shift to happen, there are a lot of things that we need to make possible. And some of them are even in the phase of communication between this automation and the human. And as human, we need to also, we are normally the one with the idea of being in charge of the automation and monitoring the automation. And that's true. But if we collaborate with the intelligent agent, we need also the intelligent agent to have a way of monitoring what we're doing, where we're at, and whether or not we are able to continue or not. This is also for our own safety, like for instance the possibility of a robotic arm slowing down pace when his companion working side by side is not able to keep up, or is in need of a break, or more importantly, like imagine a control room operator that is being overwhelmed for a very long period of time, and that could be even detected by keeping your pupil size at maximum dilation for a long period of time. Could be a way of telling the automation, look, my human collaborator needs a help, please supervisor, come over and give him some help or support, etc. And in fact, I think this is where we like to move towards, and the capacity for the analytics coming from eye tracking can actually provide some leverage towards that. In explaining collaborative intelligence and explaining our point of view is that we keep a human-centric approach, as dictated by the European Commission. In this context, we think it's important that we keep in mind the fact of the human contribution, the fact that there is a collaboration. So a human has a very strong contribution in relation to train, explain, and sustain the AI models. And at the same time, we acknowledge the fact that the AI has a role to play in well, we all see this in amplifying, in the interaction, and sometimes even in the embodiment part. And if you think about it, eye trackers are part of this, like they are effectively part of the embodiment and part of the amplifying and even part of the interaction. So they cover a lot of the things that we're interested in. Another important element in this is that we're actually working in a very specific context, and it's the one of safety critical system. So a safety critical system is basically in a context where any human error or any issue with safety performance can lead to potential accident, an accident that we rather not see happening. Therefore, for us, it is important that whatever technology we test and operate, it's stable, safe, and potentially has a role in enhancing functional safety even further. And in that sense, we developed a design of experiment that is able to provide us the data regarding the human performance, the system performance in unstable condition, for instance, or in condition that needs to be improved, and test this idea of the human in the loop. Because as you know, in the EU AI Act, it's important that the human is able to keep an oversight of what the system is doing, and therefore being kept in the loop is critical to that effect. And for us, even the data coming from eye tracking could be one of the important elements in this sensorized modular environment that we want to test, that can able to give us some information about what information is human capturing, how much is in or out of the loop in the sense of even underload or overloaded, or what is or her keeping attention to. The fact that we are doing this in a context of a European project with many researchers collaborating together gave us the scope of building some living lab, we call it like that. So where we had the capacity to collect data from a multisensorial input. So we were able to compare with mixed methods. So for instance, we were able to compare performance data, actual ground truths on operators' performance, with the data that we collected from the eye tracking, the EEG, in some cases even the heart rate, the motion detection. And in general, these were all there even to collect data for subjective data from the participants themselves. At the same time, we were able to actually objectively monitoring how the system was doing, how the interaction was affecting, for instance, the automation in a control plant or in robotics, and how these affect the combination of the two to work towards a safety outcome. And we were kind of trying to test how even the user experience part was part of this package. So this is an example coming from one of the researchers that is actually not here, Chakra, in the context of naturalistic learning in human robotic collaborative environment, but it's actually very representative of many of the design of experiment that we captured. So we had the data coming from the system itself. We had subjective data that we collected before and after, and sometimes during, for testing also elements that had to do with situational awareness of the participants. We had in some cases motion tracking, and the eye tracking was very important part of this, not only for mental workload like shown in here, but also for testing of what happened in terms of when we modify the human-machine interface. What information is important? What type of representation is more helpful for an operator to carry out their task safely? And also how that correlates with other measurements that we take. In the context of CISC, we had three main areas of research, a living lab, we call them. The first one is in human-robot collaboration, and Inesh is going to be presenting about telerobotic operation and the design of an HMI, because paradoxically or interestingly enough, there are a lot of standards dictating how an haptic device should respond to the interaction, and very little about what a 2D representation of a 3D environment that is remote in respect to an operator should convey that information to enable him or her to act as much as they can in the best possible way. So Ines has some interesting example from that, and some interesting lessons learned also due to the fact that It's very hard to connect the data coming from all these different sources, and sometimes the problem with eye tracking is also how well it connects or synchronizes with other form of data that we need to collect. Then we had the other living lab on assisting human decision making in control room operations, and this is what Tamara hopefully is going to be presenting about, where we had the decision support system, and even there we were testing about how that decision support system was interfacing with an operator, but in general also other elements of decision support in the current HMI were or not affecting their capacity to respond to alarm and the status of alarm overflowed sometimes. And last but not least, Enrique will be discussing his work on mental workload in air traffic management task. He's also been very much like the others, been collecting and correlating data that is the objective human performance and the objective condition of the task, like how busy a sector is, with subjective workload measurement. And interesting also, he has been working extensively with voice recording and labeling and data regarding the communication, together with eye tracking. I think all this collection of data offer eye tracking on its own will not be able to give you the rich picture that we need for this context. That's why it's important that we always keep in mind that in our lessons learned, one thing that we can tell you is that a good design of experiment is the key to achieve what you need to achieve. And also thinking about even before you start the experiment and what you want to analyze when you get it. So what does it look like? The data set that you want to have from your eye tracker, for instance, and how does it match the performance that you need to observe for the good or bad situations that you want to avoid or mitigate or use the data for. So without further ado, I'll pass the ball immediately to the others. I think, Marisa, if you help me with that, because we give more time to discuss the results.
Thank you so much, Dr. Leva. That was a great overview, and we're really excited now to learn more about the specifics. So I'm going to invite Inez here, and her presentation is next.
Hi everyone, good morning and good afternoon. So thank you for the introduction. I'm gonna start to talk about the use of eye tracking for testing HMI, which means human-machine interface configurations in telerobotic applications. If Marisa could skip to the next slide. Thank you. So teleoperation, which can be defined as the remote control of either robots, machines, or other devices, is usually used for applications that have dangerous tools or are applied in dangerous environments, such as space telerobotics, space teleoperations, military operations, search and rescue operations, and also surgery. If you could skip to the next two. Thank you. However, despite the recent development of teleoperation systems and the technology for teleoperation is still challenging due to the remote situation awareness that we have, the limited situation awareness that we have from the remote environment, and the limited control options that we have. And so in research to deal with these limitations, there have been a lot of solutions proposed to augment this technology. And for example, add several camera views to increase the field of view. If you could skip 2 times. Thank you. Other interfaces used, for example, virtual reality, augmented reality, or mixed reality interfaces that allow us to add other digital functionalities in real time. And if you could skip 2 more times. There's also been a lot of research on using different input devices that allow to simplify the control schema. If you could skip next. However, this has been more work focused on developing the technology itself, and there's been a lack of work on user-centered development of these interfaces that can support the use of this technology for daily use by non-experts. And this can also be translated to the industrial to industry by improving the usability of the interfaces and reducing training time of the operators. So next. Our goal was then to use user-centered interface development for a specific case study, the case study of medical device manufacturing, if you skip next, commonly requires the manipulation of miniature and malleable objects, precise and fine movements, in some cases low volume production with high customization and a sterile environment that is hard to keep when the human is on site. And so our goal was to develop this CISC lab to develop human-in-the-loop teleoperation, telerobotic solutions that can combine the benefits of robotic systems with the expertise of operators for this specific case study. So we had three main goals. So the first was to design HMIs for teleoperation with user-centered principles in mind. Then to assess the impact of different teleoperation interface factors on operator state, behavior, and performance. Usually, performance and behavior metrics are most commonly used to assess interface design, but we want to have a user-centered view of this design process, and so we want to look also at the operator state. And finally, we did user experiments to evaluate the proposed designs using biosignals, in our case, EEG and eye tracking, which I will talk more about later. So here, I show our experimental setup, which shows an operator station where the controller uses a pen-like controller and the visual interface to control a robotic arm that has a hot wire attached to it at the end of the robotic arm that will be used to perform a cutting task on a styrofoam workpiece. So this is a representational cutting task of an actual use case in medical device manufacturing process. And in the remote robot station, you can also see there are two cameras that are pointing at the workpiece. They are USB cameras, and then another one that is attached near the hot wire that is pointing downwards. And so the operator needs to use these three camera views to be able to control the robot, see the remote environment, and do the task. If you could skip next. Yeah, so we designed 4 different HMIs based on 2 experimental hypotheses. In the first HMI, the interface A1, you can see it's a simple split screen design where you can see there are the 3 camera streams and also a virtual environment. So the virtual environment is similar to a digital twin that the operator can interact with, change the perspective, and can better see if the robot is near collision with any of the objects in the remote environment. In this case, there's a fixed control frame that is fixed at the base of the robot. So the commands that are sent through the controller will be translated to the robot with respect to this reference frame. And we compared this interface with interface A2, which is quite similar, but in this case, the control frame is aligned with one of the views, and the operator can click on the camera view that they want to use to control the robot. So we hypothesized that with a fixed control frame, there's no overhead task of having to switch the control frame during the task and having to remember which one to use. But with a view aligned control frame, the operator is more able to, so it doesn't have to do the mental transformation of how the robot will move when using other cameras, when visualizing the other cameras. So if you could skip next to the second hypothesis. So in hypothesis B, we compare interface B1 that only shows one camera at a time and the virtual environment aligned with it. So here we hypothesize the operators will use more the virtual environment to compensate for the lack of visual information. And in this case, they also have to interact more with the virtual environment if they want to change the control frame, the view that is being used, they need to click on the camera in the virtual environment to switch it. And we compare with interface B2, where we show again all 3 camera streams at the same time, but the one that is being used as the control frame occupies a bigger space in the interface. If you could skip next. To evaluate these interfaces and the hypothesis, we collected user performance data, more specifically cut quality and task completion time, also user behavior data, specifically the visual use of the interface with gaze data and also physical interaction with the interface. Also user state data that can be shown next. So as I mentioned, EEG, which is electroencephalography that measures electrical changes in the brain, and also eye tracking. So this gives us data that are indicators of different user state metrics. And we also did questionnaires so that the users could report their own state, their own perceived state. And if you go next, here I show why we chose EEG and eye tracking. So based on a theoretical neuroergonomics framework proposed by the He et al., they map different mental degraded performance states to 2 dimensions, physiological arousal, which is our general physiological activation level, and task engagement. And both EEG and eye tracking are good modalities to monitor these 2 psychophysiological dimensions. So with EEG, we have a finer temporal resolution, and we can use spectral power indicators of mental workload, engagement, and arousal index. With eye tracking, we get some behavioral information as well, and we can use pupil diameter, average fixation duration, blink frequency, and blink duration that have been shown to be indicators of mental workload, arousal, engagement, and also fatigue. And so next, I show how we used Sobe to design the experiment and conduct it. In the next slide, here I show how you can set up. You can set up each step of the experiment. So we started with a demographic questionnaire, then eye tracker calibration. Then we did 3 trials for each condition, starting with the baseline recording, then the screen recording of the actual task, and then we did the questionnaires to assess the user state. We did a within group experiment design with a total of 26 subjects, 13 for each hypothesis. And next I show how we synchronize the 2 modalities. So we use LSL, which is Lab Streaming Layer, is a framework that allows the synchronization and streaming of multiple data streams. And in this case, we use them to stream keyboard markers that would indicate the start and the end of each task, each trial. So these markers were saved along with the EEG data in the same file. And also with the WiproLab, the data that is directly exported from the software also shows where these keyboard events happened. And so we can use these markers, these keyboard event markers, to synchronize the 2 modalities. And so next, I finally show some results. So I'm just going to focus on eye tracking and just show a few of the results. Regarding hypothesis testing, we compared fixed control frame interface with the view-aligned control frame, so the interfaces that changes the control schema. And we saw that actually there was almost no significant difference in the eye features, only on the mean blink duration, which was higher with interface A2 than interface A1, which could indicate higher mental workload. However, this was accompanied with a higher perceived performance and also higher actual performance. The quality of the cut was better with A2 than interface A1. But when we go into the actual change of the visual configuration of the interface, we did see more significant differences in the eye tracking features. Specifically, pupil diameter, the mean pupil diameter was higher with interface B2, the blink rate was lower with interface B2, and the fixation ratio on the virtual environment was higher with interface B1, which we were expecting. And the reported frustration with the questionnaires was higher with interface B1. However, despite these differences in user state indicators, in the use of the interface and the reported state of the user state, this does not translate to the user performance. So there was no significant difference in task time and also in the quality of the cut. And next, here I just show that there was a tendency, but this tendency was not significant. And so when we compare these results, and considering that between A1 and A2 there was a significant performance difference, we see that different interface design factors affect differently both user state and user performance. And we cannot use just one of the type of metrics to assess how the design of the interface can affect the user and the task itself. So next, thank you. Here I just show, we looked at how the interface was visually used to see if this could explain the differences in performance. So at least with interface A1 and A2 that you see on the left, there doesn't seem to be a big difference in the distribution of total fixation duration. And so in these two interfaces, there was a big significant performance difference, but with these aggregated values of the use of the interface, there doesn't seem to be a difference. And then we also noticed that across all interfaces, the visual environment was almost not visually used, and also they didn't interact that much with the virtual environment, which was surprising because some of the subjects were almost colliding with some of the objects in the virtual environment. So they could have benefited from the use of the virtual environment, but they consider it to be cumbersome and to not have such important visual feedback as the cameras. And so we hypothesized that if we combine it with some other support tools, such as collision avoidance tools, it might be better accepted by the subjects, by the users, and be more useful for them, or considered to be more useful for them than as we have it now. And next. So here I just showed that we looked at the actual ratios of the use of the cameras as control frames, and also the fixation ratio in each of the areas of interest of the interface. And we saw that mostly interface B1 was the one with most different use values of the interface areas compared to the other interfaces. And we confirmed that the difference in performance between A1 and A2 does not come from the difference in the visual use of the interface, but from the difference in the control schema. And yeah, just to finalize, we looked at the correlation between the eye features and performance metrics across all conditions and all subjects. And we observed that the mean pupil diameter was negatively correlated with task time, and blink rate was positively correlated with task time. And this is interesting because there was another study where the drivers performed a task under time pressure, and they also showed the drivers that performed more efficiently also showed higher pupil diameter and lower blink rates. And so this has been associated with more efficient task performance in terms of task time. And so it was interesting, we also had a similar result. And so finally, to conclude, in the next slide, we conclude that physiological indicators are sensitive to different teleoperation design factors, and that eye tracking metrics can be employed for more task-independent user performance state evaluation, so more task-independent compared to task performance metrics. But in future work, we also have to analyze how the gaze behavior and interface configuration use is different at different task stages. So right now we just analyze across the entire task, the entire trial. But in our task, we do have two different task stages. So the first one, they have to align the robot with the workpiece, and then the second stage is the actual cut, which have different task demands. So we also want to look at this in future work. And this is all from me. And if you have any questions, just let me know, and I will answer at the end. Thank you.
Thank you so much, Inez. That was really, really interesting. And I know we have a lot of clients who try to combine eye tracking with other psychophysiological modalities and maybe even subjective measures. So I hope that we get some great questions from maybe people in the audience who are interested in doing that and get some advice. So that's fantastic. Thank you.
Thank you.
And next we have Dr. Amar Abbas, and we are looking forward to hearing from you as well.
Hello, everyone. Thank you, Marisa. So, I will today be discussing a project that I was part of, and our goal was to prepare an AI-enhanced decision support system, specifically for control room operators in chemical process industries. And there were several researchers and professors from different organizations involved in this project. And the main goal of this project was to how to aid the operators in such a scenario where they are dealing with so much alarms that are coming up on their screens, and they are becoming overwhelmed with that alarm overflow. So we tried to create in an AI enhanced decision support system that can aid them during that alarm flood scenario and suggest them the common mitigation strategies. So starting with the overview, we tried to prepare. We had a simulation environment of a formaldehyde process simulator developed by Politecnico di Torino, and what we had there were three different screens. The main screen where the user could see the overall process diagram, and then once they could click on individual, we call it mimic, like individual part of the subsystem of the process plant, they could see specifically what is going around in that part of the simulation or of the plant, and then they can control if there is any anomalies, they can control and avoid that anomaly. And at the right there were different support displays, such as different kinds of alarms popping up with the different criticalities, the trends, the graph and trends of different process variables, the screen procedures that they can follow to avoid the anomalies, and then the AI enhanced decision support that gives the condensed suggestions to the operator. So we use different physiological and psychological measures such as eye tracking, the EEG, and the watch to measure the response of the operator to the alarm overflow, and to see the performance of the operator in such a scenario. So in this experiment, we used Tobii Pro Glasses 3, that was wearable glasses, and they could see the entire environment, and we could select the different regions of interest to collect the data for analysis. And the objective of this experiment was to investigate the impact of decision support systems on control room operators in such safety critical scenarios, and also to analyze the different factors that impact its ability to perceive and then respond, such as how the operators can conduct the actions on the monitor, like kind of a human computer interaction logs when such critical alarms occur. And so there were four different groups of participants with different level of human machine interaction support, and three scenarios with different level of complexity. So each group had an increment of the support that was provided. So such as group one was the baseline group that didn't have any alarm prioritization colored with the criticality of that alarm. They had the paper-based procedures, and they didn't had any AI decision support. And then with the group two, we provided them with alarm prioritization. With group three, we also added a screen-based procedure so that they could directly look at the screen and click on the mitigation strategies. And with the group four, along with the screen-based procedure, they also had an AI decision suggestion box that gave it a condensed kind of decision support to the operator. And starting with the scenario, so the scenario one was the very low complexity with no alarm flood, and then with increasing complexity to scenario two and scenario three. The scenario three was the hardest with the alarm flood, and the operator had to perform the action as fast as possible to avoid the plant to do either to explode or emergency shutdown. So what we the analysis that we did, the strategy that we took was to collect the time of interest. So in the whole video, we segmented the video into different time of interest, such as starting with the baseline overview, where the user would be just observing the situation, and then there were no alarms occurring. And then when the first alarm occurred, that was the start of the second time of interest. And then at the start of the alarm overflow, we had a third time of interest. So we segmented those times in those segments for all of the users to do the analysis at the end. The goal was to observe what was the response of the operators in these different times of interest, and then the baseline was basically to just correct those values and adjust those to a nominal value. And we also created some different areas of interest, such as the main overview display, or the mimic display, or the different support systems that were there to more condense the analysis and the data that we collected through the eye tracker. Going to the comparisons and cross analysis. So group two, that had just the paper-based procedures, and comparing it with group three, that had a screen-based procedure. What we found from the analysis was that group two had longer saccade amplitudes and duration, that suggested that they had less search difficulty but decreased processing capacity than the group had a screen-based procedure, which possibly explained by shorter fixation durations. And then with group three, they exhibited longer average fixation duration and shorter saccade parameters, and that indicated that deliberate processing and less divided attention, but also potentially difficult and increased visual fatigue. Then also we concluded that the group that had a screen-based procedure had significantly higher average pupil size, that suggested increased mental workload, while the group with a smaller pupil size could be due to the luminance effects. So there were also different lighting conditions and different setups that were involved, and we had to normalize the situations according to those changing environments. In comparing with the group three and group four, it can be observed. So at the left, we can see group three that had a screen-based procedure, and at the right is the group four that had an AI-based procedure. We can see that in the less complex scenario, group AI, the group four focuses more on the specific correct control strategy, such as controlling the lever at the left here, and mostly pays attention to the AI control suggestion, as shown here. So this is the specific control value that is suggested by the AI system. Then doing the so our main objective here was to do cross analysis with different data that we gathered, such as the questionnaires or their human computer interaction logs, such as recovery time, reaction time, response time, etc., and to compare all of them together to come to a conclusion that what did these two different groups suggested at the end. So as we can see here, like different things that these values suggest, such as the recovery time of group two three was higher than group four, and if we look at the different eye tracking parameters, saccade amplitude was higher. Saccade amplitude for critical alarm and also for the overflow was higher for group three than the group four. However, the velocity was higher for group four that had AI decision support rather than group three. and the pupil diameter for the group with the screen procedure was higher than group 4. We also did some correlation analysis to see if there were some correlation between the eye tracking parameters and different parameters that we extracted from the data set, such as the pupil diameter was directly correlated with the number of alarms that occurred, or the velocity of the overflow situation was directly correlated with the number of subsystems that they open. So this suggested some of the hypotheses that we had earlier, that does these eye tracking matrix can be an indicator of different kinds of performance metrics that we can observe at the end. And if we look at the analysis within the participants for the group with the AI support system, we observed that there were two different participants. So it was observed that the participant that follows through AI suggestions tend to solve the problem earlier with a lesser task load. And with the scenario for the hardest scenario where there was alarm overflow, this case was opposite. But the participant that followed only the AI suggestion had a lower situational awareness, because they just look at what the AI was suggested and what was directly the control to be done. They didn't had enough situational awareness of the scenario. So our current ongoing research direction is towards creating a real-time performance monitoring. So we could the goal of this project was to analyze in an offline way the different eye tracking matrix, and then if it correlates with different performance measuring indicators, and then at the end we would try to create a real-time performance monitoring with this eye tracking data. And that's all from my side. Thank you.
Thank you so much, Dr. Abbas. That was really interesting. I noticed that we already had some questions coming in. So for everybody in the audience, you can keep your questions coming in now, or we're going to address them after our next presenter, which will be very soon. So Dr. Enrique Munoz de Escalona Fernandez, please join us. And we're excited to hear about your work as well.
Oh, sorry, can you share again the screen with me? Okay, yeah. There you go. You can see my screen now, I guess. Okay, thank you very much, Marisa. Good morning or good afternoon, everyone. So I'm going to start now with this brief presentation that I've titled Research Experience Using Eye Tracking Technologies. So this is the summary of this presentation. I'm going to do a brief introduction, then I will talk about my research experience using eye tracking metrics in the air traffic management sphere. Then we'll talk a bit about my research experience using eye tracking metrics in laboratory, and then we'll see a brief conclusion. About myself, I studied a bachelor degree in psychology in the University of Granada. Then I did a master degree in cognitive ergonomics in the University of Lisbon. Then I did the PhD in cognitive ergonomics and human factors in the University of Granada. And well, the last thing I did is a postdoc in modeling mental workload of air traffic controllers in TU Dublin in collaboration with CRIDA. CRIDA is the Spanish Air Traffic Management Research Center. So about my research experience in human factor, I've been working with CRIDA for 9 years. I also have been working in the cognitive ergonomics group of the University of Granada, and nowadays I'm a member of the human factors in safety and sustainability of TU Dublin. So today I'm going to talk about how to use eye tracking technologies for assessing performance perception and also mental states, but I'm going to focus a bit more on how to assess mental states and more particularly mental workload. Okay, so I'm going to do a brief introduction about this. So what's mental workload? The traditional definition of mental workload is the amount of mental resources which are required to perform a certain task. The problem with this traditional definition is that it does not consider the human factor. Okay, so nowadays we've got a much better definition which defines mental workload as the result of dividing demanded resources by available resources of the person. Okay, so demanded resources depends on task complexity. okay, is what we call task demand. So the higher the task complexity, normally the higher the mental workload. But the mental workload is also going to depend on the available resources that that person has got, okay? And those available resources depend on the activation level of the person, and we're going to find individual differences, right? Depending on the level of knowledge, on the level of expertise, on many other factors, such as, for example, if that person slept good that night, etc. Okay, so we will always try to keep a balance, right, between demanded resources and available resources in such a way that it does not endanger safety, health is not affected, and satisfaction can be maintained. Okay, but why is it important to measure mental workload? Well, because we have to have a proper management of mental workload, right? We know that overload can lead to physical, psychological, and social problems, whereas on the contrary, under low conditions can lead to the risky situation of being out of the loop. This happens when this happens, you start losing situational awareness, you start mind wandering. Okay, so we know that all of that will lead to poor performance, and we know that poor performance can result into dangerous and risky situations in many fields, such as, for example, in the air traffic control field, increasing the likelihood of the occurrence of accidents, right? But it is not only a matter of security, which of course it's the most important thing. It's also a matter of productivity, because we know that having a good management of mental workload levels will also be advantageous to increase the productivity at work. But now the good question, the difficult question is, how can we measure mental workload? So mental workload is a psychological construct. That means that it's intangible, right? We can't see it, we cannot touch it. So for measuring it, we have to try some indirect measurements, which we call the three primary measures of mental workload. So these three primary measurements are subjective measurements, which are measured by questionnaires and a scale. Then we've got the performance measurements, which is the quantity and the quality of performed tasks. Normally, when as task demands get higher, with higher mental workload, there's a decline in human performance. But we can also measure psychophysiological responses. Okay, so the psychophysiological measurements are those measurements which normally reflect the central nervous system activation level. So there are many different types of psychophysiological measurements. We can measure the brain activity using the EEG. We can measure, for example, the heart and breathing rate. We can measure the psychogalvanic response. We can measure voice parameters, such as the fundamental frequency of the voice. And we can also measure ocular parameters, okay? But how do we measure ocular parameters? For doing that, we have to use the eye tracking technologies. The eye tracking technologies is a technology that allows recording the eye behavior, right? So it allows, on the one hand, tracking and collecting gaze behavior, so where are you looking at, as well as other ocular measurements which are related with human performance, with perceptions, and with mental states. So among different measurements, we can measure, for example, the gaze mapping, where is the person looking at, right? The pupil dilation, the blinking, the number of blinking, the duration of blinkings, the number of fixations, the saccaded movements, etc. So there are two main groups of eye trackers. So you're going to choose one or another depending on your objective and on your needs. So we have the screen-based eye trackers. The main advantage of these eye trackers is that they've got a high level of resolution and a lower level of intrusiveness. But the main disadvantage is that they've got lower mobility. You cannot move around, okay? On the contrary, the mobile eye trackers, the good advantage is that you can move around. It's got higher mobility, but the disadvantage is that they've got lower resolution and a higher level of intrusiveness, right? So depending on your needs, you will choose one or another. For example, in my field, for tower air traffic controllers, we will use mobile eye trackers because they have to be moving around. And for example, en route air traffic controllers, we will be using a screen-based eye trackers because basically they're seated in front of the radar screen. Okay. So how can we measure mental workload using eye tracking? Well, two different ways. So first of all, we can measure the central nervous system activation level using the pupil dilation measure. So the logic behind this is simple. So when there is an increase in task demands, we need to have an increase in psychophysiological activation in order to cope with that increase in task demands, and that will be reflected as an increase in pupil dilation. But we can also use other ocular measurements to assess mental workload. Why? Because the ocular behavior is going to change depending on the situation, right? So, for example, during high mental workload, we will see the following. The higher mental workload requires greater sensory processing. So for this reason, the visual behavior is unconsciously modified to facilitate the entry of greater visual input. So what are we going to find? For example, we're going to see that the number of blinks and the blink duration decreases with higher task demands. We're going to, because you need to process more information, so you blink less and for less time, right? Then the number of fixation and the number of saccade is going to increase because you will be searching for more information around. Then the fixation duration is going to decrease because you spend less time in each spot, right? And then there's the visual field gets narrowed. It's something that it's called tunnel vision. Of course, this ocular behavior is going to depend on the task that you are performing, right? But this is something common that in literature research we've seen that normally happens. So now I'm going to talk about my research experience in the air traffic management field. So here we can see some correlations between ocular measurements and the instantaneous self-assessment scale, which is a subjective measurement scale during simulations with real air traffic controllers. So here we can see, for example, how the number of links and the blink durations follow a similar pattern. So here we can see the subjective mental workload from 1 to 5. 5 will be a very high mental workload, 1 very low mental workload. So the higher the mental workload, then the lower the number of blinks and the lower the duration of blinks, okay? And the higher the mental work and the lower the mental workload, the higher the frequency of blinks and the higher the duration of blinks. And here we can see as well how the number of saccades and the number of fixations increase as task demands gets higher. We can see the correlation with the subjective mental workload measurement, how as you've got a higher value of subjective mental workload, there's an increase in the number of movements and in the number of fixations. Okay, but we can also use eye tracking for measuring other things, such as, for example, the performance, right? So this is an example of how can we use the eye tracking technologies to measure the performance of, for example, an air traffic controller, and it is the response time. So, for example, in this particular scenario, there was a message, an important message that was prompted here in this auxiliary screen located at the left-hand side of the main screen. So we can measure that, for example, that air traffic controller took 12.4 seconds to look at that important message. Okay, so that will be the response time, and that is a performance measurement. But we can also use the eye tracking technologies to see how the human perceives in the system, right? So we've got many different measurements. For example, the gaze mapping, you can see where is the person looking at and what's the pathway that that person follows. We also have heat maps, areas of interest. Okay, so we're going to see a couple of samples here. So this is a gaze mapping example. So with this, in this situation, we wanted to show that it was not a good idea to use a touchpad as a method to input data into the system. Why? Because you have to be switching your attention once and once again from the main screen to the touchpad because you don't have tactile feedback. Okay, so that's a way that how we can see that it is not a good idea to do that. Then this is an example of a heat map for 50 minutes. So during 50 minutes, we can see where the air traffic controller looked at. So normally what that person did is to focus on the radar screen, but we can figure out things like, for example, that this tool over here was not used, okay? So it's a very nice tool to see where is the person focusing his or her attention during a certain period of time. Okay, and now I'm going to talk about two different studies that we did with ocular measurements. So in this study here, we wanted to validate whether ocular parameters collected using different eye tracking devices can be used to measure mental workload. So we have two different eye tracking devices, portable eye tracking devices. So we wanted to test this. Okay, so we use the multi-attribute task battery 2 task. This task has 4 different subtasks, and you can modify the level of task demands. So we had as independent variables task demands with 4 levels. Then we had 2 different lighting conditions, low and high lighting condition, and we used 2 different mobile eye trackers. As dependent variables, we collected different ocular parameters, and we collected the subjective mental workload every 30 seconds. Sorry, I'm going to drink some water. So here are the results of this study. So we can see this is the subjective mental workload scale. We can see that as task demand increases, there is an increase in subjective mental workload in every condition. It's something that is normal. We were expecting that. Here we can see how pupil size gets higher in every condition, but we can see that there are differences depending on the lighting condition for sure. So low lighting conditions, pupil size is higher than during high lighting conditions. But in every case, we can see that there is an increase in pupil size. Then about number of blinks and blink duration, we can see a similar pattern. We can see a decrease in the number of blinks and a decrease in blink duration and as task demands increase. And about number of fixation and number of saccades, which are similar measurements, we can see how all of them, how these measurements increase in all the conditions. Okay. And finally, the fixation duration also decrease as task demands increases. And this is another example of another research that we did for measuring mental fatigue. So in this research, we wanted to see if we could use the fundamental frequency of the voice as a measurement for mental fatigue. So basically, it was a 2-hour task. So we have 4 different measurements here. We have a performance measurement, subjective, and two different psychophysiological measurements. So there is a performance decline as time goes by. There is an increase in subjective fatigue as time goes by. We can see how pupil size gets lower, so there is a decrease in the physiological activation as time goes by, as resources get depleted, right? And there's an increase in the fundamental frequency of the voice, which was what we were trying to find, okay? So finally, the conclusion is that we can indeed use ocular parameters to assess the human behavior, right? For doing that, we need the eye tracking devices. So we can use ocular parameters as reliable measurements for performance, perceptions, and also for assessing mental states. Thank you very much.
Wonderful, thank you. That was great. So now, as we're wrapping up, I'm going to have all of the presenters please come back, turn on your video and your microphone. We're going to get started with the Q&A. For everyone in the audience, please keep your questions coming in the question box in GoToWebinar. Thank you so much again to all these amazing presenters. I'm really excited to begin this discussion. So again, we'll get to as many questions as we can in the time allotted, and I hope that everyone here is inspired by the research that you've heard today. While we're getting started, I'm going to ask a quick question of the audience. So our question for you is, have you used eye tracking in your research? So is there anyone here who's currently using eye tracking, people who have used it in the past but they're not using it now, or people who are potentially going to use it in the future? You should be able to just answer quickly right on the screen. So it looks like so far most of you are currently using eye tracking. That's great. After this webinar is done, you will also receive a survey. We would love if you would provide a little bit more information to us about the type of eye tracking that you use, the type of fields, and provide some feedback about this webinar. So it will come, I believe it will come via email. So again, please, we would love any feedback that you can provide to us to help with future webinars like this. Give it a couple more seconds for anybody else who still wants to vote. Okay, great. So here are the results. About half of you currently use eye tracking. A small proportion have used it in the past, but not now. And a large proportion of you also, about 40%, have not used it yet. So I hope that you get inspired by today's presenters, ask some great questions. So let's get started. Before we get started, I also want to describe what's on the screen. You see 2 QR codes. The one on the left says reach out and talk to a Tobii expert. For prospective customers, you can contact us at tobii.com. class dash contact. So if you are not a customer yet and have questions for our sales team, that's the easiest way to get you to our sales team. For existing customers, you can access us through the Connect portal at connect.toby.com. And then the QR code on the right is our link to funding support services. You can also email me directly, as I said before. So please feel free to reach out. So my question to start is for all of you here. All of you have combined lots of metrics. You talked about combining performance metrics, reaction time, objective, cognitive metrics like eye tracking, maybe even EEG, GSR, heart rate, as well as some subjective user-reported metrics. So my advice for you that you can hopefully share with our audience is what are some tools or tips or tricks or pieces of advice that you can share when trying to combine large amounts of data and metrics like this. And let's just start with you, Maria, and we'll go through the order and that you presented. So I'd love to hear some advice that you might have about combining large amounts of metrics and data like this.
Hi. So Marisa, I think from the perspective, it depends very much on the application. So from the perspective of what we heard today, Inesh didn't speak about it, but we had awful trouble. It was very hard to synchronize I think they had awful trouble synchronizing the EG, the eye tracker, and then other form of metrics, and also the actual timing of the experiment. Therefore, when you have the log of the performance metrics, how that synchronizes the data, for instance, that you got from the eye tracker. And Toby offers a very, very useful environment that Inesh has even tried to use, and she can provide that information herself about how that was done. In some of the research questions before and after the experiment were organized according to that a little bit. For the Living Lab 3, we couldn't do this, so the synchronization has to be all manual, and Inesh also had to work manually heavily on the results of the eye tracker data, because basically we're talking about a situation where you cannot really map a static HMI or a stable HMI. It's not, HMI is never static, but in this case it was even changing, in the sense that we had to actually test how a configuration of a set of screens and display of information can compare to another that is different. So that basically she ended up having to do that manually, to go through all the individual recording of all the participants to gather for each one of them what they were looking at when they were performing well, what type of interface they were actually using in different interval of times throughout their experimental conditions. So without going into the details of comparing this data, the most difficult part is anchor points for the eye tracker data with performance. That is crucial for human factor research. So the performance data is what I would say has priority over everything else. And the performance data is, as I said, is difficult in the sense that there is no stable mechanism for synchronizing, for instance, a simulator log with the recording of the eye tracker. The good thing is that actually, but it's manual work of someone going through the recording and seeing what he or she, the participant, is looking at while being at certain point in time of the experiment. And also Mark can tell you this. There was no free meal, no easy recipe to get, and in our case the recording sometimes are heavy. Our computer didn't have enough memory and kept crashing. So these are the untold unfashionable part of the story that gives you pain and nobody discusses when you're presenting the final outcome. But the thing is, it's important that what I was saying earlier, like it's important that you kind of think in advance what success looks like, what you want to see out of that recording before you actually get to see it, because and do a little bit of testing, because it is painful to go through all the individual recording, and most of these guys have done that. But if you can simplify things, like for instance, for Enrique, like he knew very well that he was interested in the pupil diameter, how that was correlating with the well, in previous research, it was in the instantaneous self-reporting data of the workload, but also in the metrics of, the actual sector occupancy or other things that there are less. It was less difficult because the sampling in the interval of sampling was less frequent. But in the case for Amar and Inesh, where there was a simulator or a task ongoing on a continuous basis with some changing features that needed to be actually assessed in respect to the HMI, there was no saving us from having to do the heat maps and going through the individual recording and mapping those gaze into specific points of the screen. And that is the most time consuming aspect of the analysis, in my view.
Gotcha. Yeah, I mean,
Otherwise, what do you
yeah,
think?
looking at the graph that Inez shared, I just thought, oh, I can feel all of the work and the hours behind the scenes that were put in to do this analysis of all these different metrics. So, Inez, do you have any other advice or insights into this possibly painful behind the scenes process?
Yes, for sure. Yeah, so the selection of metrics is definitely task dependent and application dependent. In my case, like I showed, I had a theoretical neuroergonomics framework that was basing our selection of metrics. Um, However, yeah, it's very time consuming to synchronize them and to collect all these data. So a possible solution is to do first a pilot study with a small amount of data, small amount of subjects, where then you can compare and remove those metrics that seem to be redundant, that share the same information, so that when you do the actual experiment, and in my case it was only 26 participants, but when there are much more participants, using all these metrics is not efficient. And so after doing the pilot study, seeing which metrics are more efficient in terms of they don't share that much information, um, then that's easier to do in the actual experiment. And so, yeah, that would be uh, my suggestion.
Yeah. So more is not always better. Keep it simple and dial in what you're really find the metrics that are going to give you the best results for what you're trying to measure. Awesome. And
Exactly.
Amar, or
And I know the. Oh, sorry.
go ahead. Go ahead.
No, I was just saying I would only suggest to do a pilot study first, because it's hard to know from the beginning which metrics will be better for each task, each interface, each application. So yeah,
Yeah,
that's it.
that's great. That's great advice. How about Amar or Enrique? Do you have comments about this?
Yeah, so I've always done manual synchronization. So normally what I do is I take 5 minutes baseline, and considering that you can always see the recorded scene, then you can synchronize the rest of the parameter of the variables. That's the way that I've always done it.
That's great.
Mhm.
Yeah, in our experiments, what we faced difficulty in was that we had a lot of number of participants, like hundreds of them, and we had different data streams coming from different devices, such as surveys, watch data, and questionnaires, and those kind of eye tracking data, and also EEG and different kind of data sources. But like if the design of experiment, like we had to do the design so as soon as possible to fix the design of experiments, because later on, if we don't have a fixed set of variables that we need to measure, then we have to remove too many of the that participants data, as that would be like we wouldn't have a complete data set if we don't have a fixed parameters for the design of experiments. So my advice would be to fix as soon as possible the 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 data streams that you would be measuring, and then to have a reliable, like a working environment. So if we, especially working with it with an eye tracker, is that if we change the system or the environment too often, then it's difficult to map back to the recordings and to the images to generate the heat maps and those kind of analysis, and to collate them together if there are different working environments in the experiments.
That's great. Yeah, keep the environment static. So actually, while you're here, Amar, there's a question. I think it was for you, but possibly also Enrique could answer. It's a question from Kirill. It's a question about AOIs. I think it's related to the wearables. So how did you manage AOIs? Did you use the dynamic AOIs, snapshot mapping, or something else? And Amar, do you want to start?
Yeah, so we had a screenshot, and then we had like a static AOIs, and then we mapped over different recordings on the same screenshot.
Okay, great. So
Yes.
just standard mapping, yeah.
Yeah, in my case it was the same. We have the different pictures, and then it's something that the software does very good. You just have to assist a little bit, and it does by itself. Yeah.
Great. Yes, that is a tool that we have in Toby Pro Lab software. It's our assisted mapping. So there is some automatic portion that you can run, and then there's a manual override. So if there's a part of the recording that didn't get mapped to a snapshot, you can add that in. So that's great that you were able to use that feature. Awesome. So let's see. Another question here is, I guess for everyone, what modalities have you had a good result in using, I guess, in conjunction with eye tracking? This person asks about TMS, EEG. I know obviously, I think Enrique used EMG, EEG, EMG, and then any data acquisition software that could help for that result. So what modalities have you found good result in using with eye tracking and these other subjective and performance metrics? So let's start with Enrique.
And sorry, I didn't understand the question. So what's I haven't used EEG.
Oh,
So
okay.
yeah. So normally I gather subjective measurements and performance measurements. So what? Sorry, what was the question?
Oh, I'm sorry. I got it wrong. Inez was using EEG. Is that
Oh,
right?
okay.
Okay. Yes. So are there other types of physiological metrics that have worked for you with eye tracking?
In my case, I actually only went for EEG and eye tracking together. Like I said, from the, the theoretical model, we chose specifically for that. And also depends on the type of analysis. So one of our goals was also um, to use the continuous data to train a model, a deep learning model to predict human performance. And so for this case, EEG can be more useful due to the higher temporal resolution. While if that's not the goal, if the goal is, for example, like I did, to assess an interface after a specific time of the use of the interface, then other slower a lower resolution, temporal resolution physiological metrics can be used. Yeah, and in our case, we used Embrain Train software for the EEG, which I didn't show that, but we also synchronized it using the Tobii Pro SDK API. And that allows us to synchronize EEG and eye tracking in the same file. So they are saved in the same file, and with also all the markers that we also use before to synchronize them and to know when the trial starts and when the trial ends. And so using LSL, which is Lab Streaming Layer, with these two softwares was actually very helpful. For this part of the analysis, I didn't show of using it to train a deep learning model.
Yes, and Brain Train we can synchronize with their systems via LSL. Some other EEG vendors that are out there, we may be able to synchronize in other ways. Sometimes it's a TTL out. For some of our vendor partners, we have more combined metrics. So if you are interested in using anything like EEG or FNIRS or TMS with eye tracking, reach out to us because we can help guide you to figure out the best way to synchronize that data. That's something that we can do. So feel free to reach out. That's awesome. Thank you, Inez. Okay, question for Amar. This is a question about the users of the experiment control room. Were they experts in the field or novices or something else? Because sometimes the difficulty in the area is involving control room operators. So yes, tell us more about the participants.
Yeah, thank you for the question. So participants were the students, bachelor's or master's or PhD students, and some of the professors. So we had two different sets of students. One of them were experts in, like, one of them had the backgrounds in chemical fields. Like they had prior experience of the knowledge of the process industries, and the other set of students were more related to computer science and food science and those kind of background.
I have a follow-up question for you. So do you think that training with the AI decision support interface would help the performance and decrease the workload? Sort of.
Yeah, so this is also what we were one of the suggestions that we got from the real world control room operators, that either to use this system in a real world environment, it is better to use as a training support for the new operators, so that they can know like how the system is operating and what are the different mitigation strategies. So the AI decision support can be more helpful in the training rather than using it in the real systems. But what we also envision is that once it is integrated in the training system and the operators are used to it, it can also be implemented in the real systems then.
Great. Dr. Leva, you had your hand up?
Yeah, no, personally, we have to be careful on this view. Okay, so the thing is this: if you have to keep in mind the example of, for instance, the some in aviation, for instance, if you learn to pilot an airplane with certain automation support, it would be very hard for you to do that task without. So
Okay.
I don't think it's a good idea for the you can have so what we study in training, for instance, is that you can have increasing level of difficulty. That at the very beginning you can have the crouch, and use it, but then you have to go without it. For us, the long-term game is to have a decision support system means different things, and there are different levels of support. For instance, alarm rationalization is a level of support that is absolutely needed. And I wouldn't ask any operator to operate without any form of alarm rationalization, because it's inhuman to have to deal with. In our example, some operators are confronted with 30 alarms in 2 minutes, 3 minutes, so it's impossible for them to attend them all. Okay, so a form of decision support that we think it's necessary is to filter out the bad information from the very important or relevant one. Okay, for us to be able to do that, okay, for this, it's useful for training, but it's also useful for normal operations. But for us to be able to do that, we have to demonstrate that such a tool doesn't decrease their level of situational awareness, but rather have a positive influence. So that's why we cannot, unfortunately. One thing that is sure is that using eye tracking data, it's very useful to see where they are looking and what they're looking at. And for instance, some of the group 4 people, they look just at the suggestion and the panel to activate that suggestion without gathering any extra information, we're probably more likely to be missing situational awareness. But without asking them, you don't know. So the eye tracker or the EEG by themselves, they don't provide you any information about their situational awareness, which is a critical or crucial performance metrics for us. Okay, while what it could be, and we haven't done it yet, and it's the next phase of the study, if we find a way to do it, and we can discuss it too also, if we can get our funding for doing it. For us, it would be very interesting to see people that have high situational awareness and good performance, and their pattern of searching for information in the screen, how that pattern differ from people that have low situational awareness, maybe less experience, and less good of a performance.
Yeah, that's very interesting because I definitely see lots of applications of like situational awareness outside of these types of um, fields. And I think a lot of what you all have talked about today, I think could be applied in medical, in construction science. I mean, I think there's a lot of cross field applications for this type of human in the loop work. Um,
One thing that was very useful to say about that we have done, not presented in this in the presentations of today, but we've done it in other. What is interesting is that having an experienced operator wearing the eye tracker in a real work environment, we've done this in manufacturing, an operator using precise machining for milling operations, and describing what he or she was doing while they were doing it. That was very interesting and relevant content for training of other operators. So the eye tracker is the eye tracking in a real world context with some talking out loud protocol was perceived immediately by the novices as, my god, because you're like actually looking at the reality through the eyes of an experienced operator that is talking through what he's doing while he's doing it. That was a very useful input. That was something that we would wish to use again in the future if possible. So
yes, the concurrent think aloud or retrospective think aloud. In this case, sounds like it's concurrent. That's an interesting protocol that we have customers use in a variety of fields. I think we're getting close to the end, but I have one last question for everyone. I also wanted to say that I was really compelled by explaining the human-centric approach and that AI is meant to be a collaborative tool with humans and not replace them. I think with the rise of AI and it becoming such a buzzword now, it's comforting to know that we're trying to make AI that works with humans and works for humans without replacing humans. So I really appreciate you sharing all of this work today. And with that in mind, my last question is, where do you see your research moving? Where would you want to see eye tracking moving, let's say over the next 10 years or so? And what are some of the dream features that would be able to help you answer more questions about the roles of human machine interaction? Let's start with you, Dr. Leva.
As I said, I have two things in mind. So, for instance, I like to see in the control room, for instance, is a place where, in terms of human factors, we currently have failed our mission in supporting parity operators, and AI as a role to play there. Not so much in providing monkey instruction or suggestion that are specific on what value to change, etc. Because also that's not compatible with the complexity of some of the scenario that people have to face, but in potentially helping differentiating, seeing the woods from the tree, differentiating things that are relevant from things that are not relevant. And eye tracking can also be useful in that sense, because if someone is looking where part of the screen that is actually giving the core information, and it's not always easy to see that, but that is a good indication of the fact that they are more likely to respond to the situation more promptly. And this is some behavioral measure that we want to be able to observe. As I said, in the collaborative space, we are so used to be the one monitoring the automation, and that's true, and that will stay that way. But there is also another element now of provide the intelligent agent being able to provide us with feedback, saying, you were not really like you were disengaged for this percentage of your task, and you're disengaged because you're probably not looking at the information you should be attending to. But this is also true in the sense that we design tasks that are extremely boring for people to attend to. And with an eye tracker, you can see that. Like, it's not human to expect someone to look at a screen where nothing is happening for 20 minutes and for them to be attentive to that. Attentive to what? That is not designed to be a task where the human really needs to be in the loop. So even for us to document this, because we have a lot of the time we have a sort of an inside bias on commenting on human error after the fact has happened, saying, "Oh, he or she should have been looking at the screen when the alarm happened." Yeah, but before that alarm happened, there were hours of nothing happening, and therefore, is that the task we want people to have? Like even for us to design systems that are more interactive in nature, that like we do for the pilots, we make them fly the aeroplane even if the autopilot fly can land it better, just so they don't lose the capacity and they are interacting with the system. It's something that we can document. The eye tracker can actually provide that view from the user perspective, so that we could see them getting bored, because unfortunately this is what is happening more and more these days.
Yeah, that's interesting. That's great. Let's keep going. Inez, what do you think? Moving into the future, and what kind of dream things would you like to see?
Yeah, I think at least in teleoperation, virtual reality is the future for sure. Although there are some issues with it at the moment, virtual reality will be the future, and also eye tracking using headsets, for example. Um, it will be very important to be able to analyze how to design these virtual reality environments, since in virtual reality there's 1,001 ways that we can design it, and we can add a lot of different functionalities. And so eye tracking is definitely essential to design it and to analyze what is actually helpful, what is not in these environments. So that is one of the ways eye tracking can help.
Great. Love that. All right. How about you, Amar?
Yeah, I think currently what we did was an offline analysis of the eye tracking videos. But what I see further is that if we could do it as an online way, if we could do real-time monitoring to the eye tracking, that would be really beneficial. If you could if you could observe and analyze in real time what is happening, and then based on that situation, we could aid the operator, or we could aid in that situation. What is the best what is the best strategy?
That's great. Yeah. All right. Enrique.
Yes, so I imagine in the future some embedded eye trackers in your working place that can gives you an index, an easy index in real time about your mental workload, maybe your mental fatigue, etc. But something straightforward for everybody, so that you don't have to analyze data and everyone can see at a glance how is the mental state of that person. That will be a very big step forward, I think, for the industry.
Awesome. Yeah, I totally agree.
Mhm.
Well, that's fantastic. Any final comments from you as the panel as we're wrapping up here?
Just on this, following up on Enrique, even EG is moving towards a form of being able to provide some self-feedback to the user. So there is nothing less empowering than someone else analyzing the data on your own performance and you not knowing anything about it. So simplifying this, like the EG, there are very simplistic form of analyzing the alpha, that tells you how relaxed you are, and they're trying to move that towards the data over alpha for the mental workload to do the feature extraction, some form of feature extraction near real time, so that you can provide feedback to the wearer, to the user. The same for eye tracking would be important to, for instance, to define some metrics, like saying, for the past ceteris paribus. So if the light conditions are the same for the past 10 minutes, your pupil size seems to have been at your maximum, because it's a feature that depends on the individual. You've been concentrating very hard for very long in this segment of your work. Is this sustainable? Was there something that happened here? Or similarly, like you have been disengaging for this amount of percentage of time during your task. Is that a problem? Something happened? Like, to be able to get some feedback that the user, like we do for the health watch, to be able to get some feedback that the user can empower the user in analyzing their own performance, it will be amazing.
Absolutely. Well, those are great visions for the future, and I hope that researchers like you and maybe even you solve those problems with our technology. So thank you so much again for for your time and your presentations, and to the audience for asking such great questions to stimulate this discussion. We hope to see you again in another webinar soon. And as always, please reach out to us if you have any questions. Have a great day. Thank you all so much again.
Thank you, Marisa.
Thank you.
Very much.
Thank you.
Thank you.
Bye.
Bye.